Now I'm going to talk about a couple of different ways in which we will typically describe or specify a signal. Recall that we defined a signal as a function of an independent variable. We said the independent variable is typically time. So the what we have then is we have a function of time, and the question now is, what are different ways in which I could write these functions of time, or I could tell you what this function actually is. Okay, so the easy way, or one of the ways in which we will use a lot in this class, is to actually write a mathematical expression for x of t. So say we can have a mathematical description. So for example, we can say x of t is sine 2 pi, or sine 2 pi times 100 times t, or let's say 200 pi t. Okay, so this is a description of a signal. When I say this, then you can find the value of x of t for every value of time. And you could also sketch this signal if I asked you to. You could sketch the signal for all values of time. This would be a signal that goes like this. So this is time t equal to 0, and this is time 1 over 100 seconds. Because the time period, I mean, this is a sinusoid of frequency 100 hertz. So the time period must be 1 over 100 seconds. Another description could be, let's say this is e raised to minus t. Then this is a signal which decays exponentially, right? So if t is 0, for example, it takes the value 1, and as t increases, it becomes smaller and smaller, and as t decreases, t becomes negative, it increases. I should also talk a little bit about what it means for t to be negative here, right? So that's fairly easy. What we are going to say is we are going to assume some point in time as the reference point, or saying time t equal to 0, and anything that happened before this time is going to be considered as negative values of t. Okay, for the sake of mathematical abstraction, we will let t start at minus infinity, and t can go to positive infinity. Okay, so this is another signal. X of t is e raised to minus t. In the discrete time case, we can do the same thing. You know, I could define a discrete time signal as x of n is equal to n squared. So what that means is I would have a signal which would look like this. So at 0 it would be 0, then it would take values 1, 4, 9 on both sides, and it just keeps going like this. Okay, so this is what I would say is a mathematical description. And one of the things that we will encounter in this class that you may or may not have seen before is that we will deal with signals which have different mathematical descriptions for different ranges of time. Okay, so to give you an example, suppose I had a let us say I have the following circuit. Okay, let's say I have a capacitor, I had a resistor, and I had a switch. Okay, and let's say I'm measuring the voltage across the resistor. Let us say the capacitor, or let's say we're measuring the voltage across the capacitor. Let's say initially the capacitor is charged to some voltage. Let's say it is charged to 10 volts, but the switch is open. Okay, and then let us say I close the switch at time t equal to 2 seconds. Then what's going to happen? And then what I want to say is I want to look at how the voltage across the capacitor changes as a function of time, and I'm going to call this actually as x of t. So here my x of t actually refers to the voltage across the capacitor as a function of time. And let's assume that the capacitor was charged to 10 volts a long time ago. So practically it's had 10 volts for a long time. Okay. So what is going to happen is this. If you think about how the voltage is going to change, it's going to be 10 volts until time becomes 2 seconds. And then the switch is closed at a certain time, right? T equal to 2. So then the capacitor is going to discharge and the voltage is going to decrease. And you know that it decreases in an exponential way, right? So it's going to decay something like this. But now you see it's not easy. Now if I ask you to write a mathematical description for this signal here, x of t, which looks like this, it will not be easy for you to write a description for x of t that is valid for all values of time. It won't be possible to write a simple expression for x of t. It's a lot more convenient to describe x of t as taking two different mathematical functions, one for all values of time less than 2. So essentially this takes the value 10 for all values of t less than 2. And it takes the value 10 times e raised to minus t over rc for all values of time greater than or equal to 2. Right? So now in effect I have described the signal because I have told you what x of t is for all values of t from minus infinity to plus infinity. But I have defined this piecewise, or I have given two different mathematical expressions for different ranges of t. So this is something that you will see a lot in this class, that these signals will be defined using different mathematical expressions for different ranges. I mean the same thing with discrete time signals as well. Another way in which we will specify the signal is to actually draw the signal directly. I could say I can have a pictorial description. So what I mean by this is I explicitly draw the signal x of t. So what I did now here is a good example. I first drew the signal and then I asked for a mathematical description of the signal. In the same way I could do another one like this. Let us say I have a signal like this. This is 1, this is time 1, time negative 1, and these are straight lines. So if I give you this signal and I told you that it is 0 for all values of t less than minus 1 or greater than 0. Now this is essentially specifying the signal, right? Because for any value of t you give me, I will be able to give you x of t. And we can also write a mathematical expression for this. This particular one, we can write a very nice and simple expression for this, saying this is 1 minus the absolute value of t if t is between minus 1 and plus 1, and it's 0 otherwise. So one of the skills that you should build early on in the class is to be able to write mathematical expressions for pictorial descriptions of signals. Okay, and often this may be piecewise. They may be specified piecewise. I think the same thing is true with discrete time signals as well. So I'm not going to separately talk about them. Another way in which you could specify signals is as combinations of other signals. So for example, I could define a signal to be the sum of two other signals, each one being specified either mathematically or through pictures and stuff like this. We can probably talk about this a little more later on. Okay, so what I want you to get from this video is the following: is how to describe signals. There are mainly two ways. One is to give a mathematical description. The other is to draw this signal and sort of give the mathematical description for this over different ranges of time. Okay, but fundamentally what I want you to understand from this is this: what I really mean by specifying the signal is to provide enough information for you to figure out what the value taken by the signal is at every value of time. Okay, that's really what we mean by specifying or describing a signal. I'll stop the video here.